Hello, my name is Hossein. I'm a PhD student at Leipzig University and the researcher at German Biomass Research Center. My presentation is the simulation of ash transformation process during silica-rich biomass combustion using FactSage software. Annually, close to 800 million tons of paddy rice is produced in the world, and the trend of production increases in order to meet the food production demand. And from this huge amount of paddy rice production, close to 20 to 25 and 40 to 80 dry base weight percentage are rice husk and rice straw respectively. These materials have higher share of ash content, which can reaches to 20 dry base weight percentage, and they have higher share of silica in their composition, which can be up to 70 and 90 for rice straw and rice husk respectively. Therefore, the combination of energetic and material utilization can be considered for such agricultural residue materials. However, these materials, compared to clean wood, have higher share of nitrogen, sulfur, chlorine, as well as silica and particularly alkaline metal such as potassium. And because of that, we have some issues in the performance of the boilers for the combustion of biomasses. And it includes the deposition formation inside the chambers, as well as the ash sintering on the heat exchanger tube of the boilers, which decreases the efficiency of such systems. And it requires some shutdowns for the cleaning of CHP plant, and sometimes it happens unexpectedly. And all in all, increases the maintenance costs for such a material. And sludge formation influences the biogenic silica quality in the boiler. Therefore, we should predict the performance and the formation of sludge formation in our materials during combustion. And we used 7 different biomasses, including rice straw and rice husk. The blended rice straw with the rice husk in 50-50 dry base weight percentage, as well as the pre-treatment method in order to produce the water wash rice straw and rice husk, and acid-rich rice straw and rice husk. For the water washing process, we employed tap water. And in the acid leaching, we use 1% weight percentage citric acid diluted with tap water. And the process was conducted at 50 degrees Celsius for 2 hours. In the ashing process, we had 2 different separate ashing procedures. One is called low temperature ash. And in this process, we applied a multi-step temperature program, which is seen here, in order to completely burn out the organic share of the fuels. And for this procedure, for this approach, we used the drying process first, and then 2 steps of main organic decompositions, which conducts in order to decompose the light and the heavy organic share of the fuels. And finally, we call this low temperature ashes. And then in a separate procedure, a low temperature ash is employed, and the heat treatment at a temperature between 600 to 1100 degrees Celsius was applied to low temperature ash in order to produce the ashes, which is called high temperature ash. And this procedure was conducted in order to study the ash transformation procedures or reactions, and we simulated this procedure. In the analysis for the fuel materials, we applied moisture content, ash content, volatile matter, as well as the elemental composition analysis for all organic and also inorganic elements. In the low temperature ashes, we use different techniques such as ECOC, CHNS, and Lawson ignition in order to measure the carbon content. And finally, for high temperature ashes, here in particularly this presentation or this investigation, we use the XRD method by applying K-alpha radiation of copper in the range of 15 to 65 degree for 2 theta. And we used Rietveld refinement method in order to quantify our results, our XRD results, using Topaz Brooker software. And the amorphous share of our material was determined using the standard, which was calcium fluoride here. And in the simulation, we employed FACSAGE 8.0 by some settings such as selecting FT oxides, FT salts, and FACS-PS of the version 2020. And then we selected the solution phases, and we deselected the duplicate gaseous, liquid, and solid species by a priority of FT oxide, FT salt, and the FACT-PS for our simulation. And I should say that the input data for the simulation were the elemental composition of our fuels, which are coming from ICP-OES analysis, and the pressure was set into 1 atmosphere, as well as the excess air ratio was in the range was set in 1. The temperature was monitored between 550 degrees Celsius up to 1100 degrees Celsius by a 50 Kelvin interval, and we included the transition points as well. And the combustion air was considered as an ideal gas in the simulation. For the results of the fuels, you see here in this table the analysis data or the measurement data for moisture content, ash content, volatile matter, the heating values, and the organic elements. And here, as you see, by applying the pretreatment, the moisture content decreases because at the end of the process we employ a drying and the drying procedure decreases the moisture content. The ash content decreases as well because the water soluble and acid leachable elements can be removed during these processes. The the volatile content increases, and the heating value increases because the share of the organic compounds increases, since the inorganic share decreases during the pretreatment process. And for the inorganic share of the fuel ashes, you see here in this the right-hand side figure. And as you see here, by applying the pretreatment, we decreases the impurity contents, particularly for potassium and phosphorus and magnesium and so on. However, by applying the pretreatment, the content of calcium increases, and it's because of the hardness of the tap water, which is used in the pretreatment process. Here you see the result for low temperature ashes and the carbon content of these ashes. As you see, by applying different measurement technique, we saw that we have almost very few content of carbon, which can be disregarded from our simulation. And therefore, we have no carbon in low temperature ashes once we start the ash transformation procedures. Here in this slide, you see the results of our experimental study and the simulation investigation as well. And as you see here in the XRD analysis data, up to 700 degrees Celsius, the material, the higher share of the material is amorphous, and we have no information from the experimental side. But from 800 degrees Celsius, the material becomes crystalline, and we can easily detect the phases in our ashes, which includes the calcium phosphate, calcium silicate, silica particularly, and calcium chloride, as well as potassium chloride and potassium sulfate, and some share of potassium magnesium silicate. And if you compare these crystalline shares with the simulation, you see there is a good agreement between these data and the data which are coming from the simulation or higher temperatures. And there are the same phases detected in the simulation. And the share of the slag increases by increasing the temperature, and the rate is high between 1000 and 1100 degrees Celsius. So here you see the result of water washed rice straw. And as you see, and as I said before, by applying the pretreatment, we bring some calcium impurities from the tap water. And because of that, besides the silica, we have wollastonite, which is calcium silicate, as the dominant phases except silica in our materials. And the crystallinity degree postpones to higher temperatures. And if you compare again the crystalline shares with the simulation, then you see a good agreement between the simulation and the experimental values. And the same information comes for the acid-leached rice straw. And we have calcium silicate as a dominant phase except the silica phase in our leached rice straw sample. And but the share of wollastonite decreases by acid leaching compared to the water washing, and the level of the silica purity increases by applying the pretreatment. And the maximum purity for silica comes from the acid-leached rice husk sample, which we detected almost pure silica for all the temperatures. And by controlling the temperature, we can produce pure biogenic silica as in the form of non-crystalline material, as an amorphous silica. So, as a conclusion, the FACSIT results are well in line with the experimental results. The rice husk has higher sludge formation tendency compared to the pretreated samples, especially at elevated temperatures. The pretreatment decreases the impurity levels, particularly for potassium, magnesium, and phosphate, and phosphor. And then, because of this decrease in the impurities, the slag formation tendency also decreases. As I said before, the calcium ions can come from the hardness of tap water, and it provides the calcium source for the formation of wollastonite or calcium silicate in our pre-treated samples. The result of leached rice husk showed that the maximum purity is coming from the acid leached rice husk, and we can reach it to 100 weight percent, almost 100 weight percentage purity in this sample. Further investigations in this field showed us that the non-thermally stable phases can form and trapped in the crushed porous structure of the material, and they can remain at higher temperature in the experimental data, which is not possible to simulate in the FACSage. All in all, the FACSage is a powerful software to predict the ash transformation reaction and the slagging behavior of silica-rich biomass assortments, although it cannot consider the reaction kinetics. Thank you for your attention.